In this video, we're going to cover section 1.7 on parallel reactions. In the reactions discussed so far, a reactant decays resulting in the formation of a single product. However, in many reactions, a single reactant can become a variety of products. Such reactions are referred to as parallel reactions. So if we consider the following irreversible reaction, in which reactant A can form one of two products. It can form product B with a rate constant K1 or product C with a rate constant K2. As we've seen previously, the differential rate expressions for the reactant and product can be developed based on this particular scheme. So if we first look at the rate of formation of A, so we look at the change in the concentration of A with time, we can equate that to two terms, where A first decays to product B with a rate constant K1, and the decay of A to product C with a rate constant K2. So these pathways are both dependent upon the concentration of A, and we include those negative signs to indicate that A is being consumed. We can factor out the concentration of A, and so we're left with the summation of those two rate constants. For the products B and C, we can express their net rate of change equal to the rate constant K1 for product B, and dependent upon the concentration of A, and for C, K2 and the concentration of A as well. Now, if we want to determine the concentrations of each species as a function of time, we begin with the same set of initial conditions that we've seen in previous examples. We let only reactant A be present at t equals 0, and everything else will not be present at t equals 0. So the initial concentration of A is not equal to 0, but the concentration of products B and C, they are equal to 0 under those initial conditions. With these initial conditions, integration of the expression for A yields a familiar form, where now we have the concentration of A equal to the initial concentration of A times the exponential. Now, the exponential form we normally will have shown up to this point has been a single pathway decaying from A. But now we have two pathways decaying from A. We have K1 and K2. So the rate constant is no longer just a single rate constant, but it's expressed as the summation of those two rate constants. Now, this equation for the concentration of A can be substituted into the differential rate expression for B and C. And if we integrate those expressions, it results in the following solutions. Now, we won't go through how these solutions were obtained, but we will comment on a few characteristics of them. So you can see that there are a couple general trends that are observed for these parallel reactions or these branching reactions. The first is that the decay of A occurs with an apparent rate constant equal to the sum of the rate constants. So we see in both instances that the decay of A to either B or C is dependent upon the sum of rate constants K1 and K2. Now, a second general trend that's observed in parallel reactions is that the ratio of the product concentrations is actually independent of time. So although, yes, the formation of C and B, these are dependent upon time and they're going to vary during the course of that reaction, we find that the ratio of these two concentrations will be identical at any point during the course of that reaction. Why is that the case? Well, if we look at these two expressions, they are similar in every other way except for the rate constants in the numerator of that first quotient. This term is identical to this term, so it cancels out. And so if we're looking at the ratio of B and C, we can simplify that to a simple quotient, K1 divided by K2. And so in that respect, it's independent of time at any point during the course of that reaction. So in addition, as we just saw, the ratio of the product concentrations is predicted to be a ratio of the rate constants K1 and K2. So this states that as the rate constant for one reaction branch increases relative to the other, the greater the final concentration of the corresponding product will be. So there's direct competition between the rate of formation of B with the rate of formation of C. So again, there's no time dependence because we see that those exponential terms in the ratio will cancel one another out. And so the product ratio will remain constant with time. So this shows that the extent of product formation in a parallel reaction is dependent upon the rate constants and solely the rate constants. So another way to view this behavior with respect to probability is that the larger the rate constant for a given process or pathway or branch, the more likely that product will be formed. So let's look at this in a little bit more detail in terms of the yield of an overall reaction or parallel reaction. So we can define the yield using the symbol phi as the probability that a given product will be formed by the decay of a reactant. Now, we can equate this value, the yield, as a ratio of rate constants, in particular, the rate constant of the reaction leading to the formation of the product of interest over the sum of all the other rate constants that are competing in that particular reaction. So this expression here, Ki, represents, again, the product of interest, the rate constant responsible for its formation, and this summation term represents every other pathway that's available to that particular reactant. Now the total yield is the sum of the yields for forming each product, and it is normalized such that the sum of those yields is equal to 1. So the sum of the yields is equal to, in this example, the yield or phi with respect to B, so the yield with respect to B, plus the yield with respect to the product C. So let's see how we can use this information to assess a parallel reaction. So let's suppose that the rate constants for our generic parallel reaction with two branches were related in the following way. That is, that the rate constant K1, which leads to the formation of product B, is twice as large as the rate constant K2, which leads to the formation of product C. So K1 is equal to twice that of K2. Now the yield for the formation of product C can be shown as follows. We have phi subscript C, so the yield of C is equal to the rate constant with respect to the formation of C over the sum of all the rate constants leading from the decay of A. So in that case, that is the sum K1 plus K2. Now, based on the previous information where K1 is equal to 2K2, we can make that substitution as shown. And so what we're left with are K2 over the sum of these two, which is 3K2. Those terms cancel, and you're left with 1/3 as your final numerical result. So 1/3 of your product distribution will be product C. And because there's only two branches in this reaction, the yield for the formation of product B can be determined in one of two ways. Because we know there's only two branches, we can simply subtract the yield with respect to C from 1. And so 1 minus 1/3 leaves us with a yield of 2/3. Or we can carry out the same calculation that we just did for product C, where we define phi B, the yield with respect to B, as the rate constant leading to the formation of B over the sum of the rate constants. Now our substitution for K2 becomes 1/2 K1. And when we calculate all that out and cancel our rate constant, we're left with 2/3. So either way, we end up with 2/3. So what this shows is that we generate twice as much B relative to C when the rate constant with respect to the formation of B is twice the magnitude of the rate constant with respect to the product C. And so that's consistent with the ratio of the concentrations at any point in time during the course of this parallel reaction, that we would expect that the concentration of B would be twice that of the concentration of C, because the magnitude of the rate constant is twice that of the rate constant with respect to C. So we've shown that if a competitive parallel reaction is truly irreversible, then the product distribution at any time will reflect the ratio of the rate constants. And so we can describe a parallel reaction in this way. The ratio of B and C is simply the ratio of their rate constants. Now, the last part of this video, I want to discuss the free energy of activation. And we will discuss this in more detail in upcoming videos, in upcoming sections, specifically the activated complex theory, where we relate kinetic parameters, i.e. the rate constant, to thermodynamic properties. Now you will be familiar with the change in free energy being equal to minus RT ln of the equilibrium constant, uppercase K. What we'll show in later sections is how we can derive an expression that relates the rate constant to the free energy of activation. And so when we talk about the free energy of activation, we're referring to the difference in free energy between the reactant and the transition state for that particular species or that pathway. So you'll just take it as given for now, and we'll come back to how we get to these expressions in later videos. But this ties in nicely with parallel reactions, so I thought I would include it earlier than later. So take it as a given for now that the rate constant for each path, K1 and K2, can be described and related to their free energy of activation. So the energy required to overcome that barrier, the difference in energy between the reactant and the transition state, that will be relative to and proportional to the rate constant in each path. So if we take the logarithm of this ratio, that will be equal to the logarithm of the ratio of rate constants. And if we look at the ratio of these two terms, this term over this term, it simplifies to this expression, where the logarithm of the ratio of the rate constants is equal to a difference in the delta G of activation. So a difference between the free energy differences of activation for those individual pathways. So a difference of a difference. So that is the natural log of the product ratio is equal to the difference in the free energies of activation for those two pathways towards B and towards C. So why am I telling you all this? Well, why we talk about this is because small changes in the relative free energies of activation can have a significant impact on the product distribution in a parallel reaction. So if we had a parallel reaction, as in our previous scheme, where there was no difference in the free energy of activation, so the delta G of activation was equal to 0, if there's no difference in the pathways, the energetics of those two pathways, we would expect a 50-50 ratio. So we would expect equal amounts of B and C, and that would lead to a ratio of 1. However, if we see a difference in the free energy of activations of only 1.7 kilojoules per mole, that's going to result in a 2-to-1 ratio of the formation of B with respect to C. So the product distribution changes dramatically even when there's just a small difference in the free energy of activation. So just a small lowering of the free energy activation for one path is going to give it a significant advantage in terms of the overall product distribution. And we see that increases even further as that delta delta G dagger, double dagger, increases. So if we have a 4 kilojoule per mole difference in the delta delta free energy of activation, then we see a 5-fold difference in the product distribution, and so on. So again, small changes in these free energies of activation have pronounced changes in the product distributions. And I should point out once again that this holds true so long as the parallel reactions are irreversible. If they're not irreversible, then we don't have as strong of a correlation between the delta delta G's and the product distribution. And we'll discuss that in the next section. So if you have any questions about parallel reactions, by all means, send me an email. Thank you.